Typically it's the volcanoes that you don't know too much about that surprise you.
And volcanic surprises can wreak havoc for air travel and transportation. That's one of the main reasons researchers are so interested in monitoring volcanic eruptions. Alaska is part of the Pacific Ring of Fire and home to about 80% of the active volcanoes in the United States. One physical volcanologist who works at the Geophysical Institute at the University of Alaska Fairbanks and the Alaska Volcano Observatory is John Dean.
We have about 25,000 people, $1 billion of cargo and equipment every day flying over the volcanoes. If you're flying from Los Angeles to Tokyo, you fly right over the Aleutian Islands. And on the average, 3 to 4 days a year, we have ash in the air traffic lanes. Ash is very bad for jet engines, so part of our job is to make sure that the Federal Aviation Administration, Air Traffic Control are aware of any potential ash hazards and that air traffic is handled accordingly.
Ash clouds are made of very small particles of rocks and gas instead of the water found in regular clouds. But any type of cloud can affect the balance of electrical charges in the air, which in turn can create lightning. It was during an eruption of Alaska's Mount Augustine that pilots reported seeing lightning. A physicist studying atmospheric electricity at the Geophysical Institute was asked to record the lightning. Davis Sentman used a special astronomical camera.
Well, we didn't see lightning, but we saw some other things. What we were able to see because of the optical response of the camera were nighttime ash flows, pyroclastic flows that tumble down the side of the volcano that were not visible to the human eye.
Sentman could capture these images because his camera can detect the infrared emissions coming from the volcano. This provides environmental information not available in thermal imagery collected by other devices. The images Sentman's camera records are remarkable, but ultimately, volcanologists are working to learn more about what happens prior to an eruption. For example, the ground often warms before eruptions, and satellite sensors can detect these pre-eruption heat patterns.
At the Geophysical Institute, we receive a variety of data from satellite sensors, mostly used for weather. We're sort of misusing the satellites to monitor volcanoes. We get images that cover the visible spectrum and then out into the infrared. And we take advantage of the different wavelengths that the satellite looks at in the infrared to try to determine what the ground temperatures are at the volcano.
Satellite remote sensing has greatly advanced the science of volcanology, but its images have significant limitations. Because a satellite is orbiting hundreds of miles from Earth, each pixel in a satellite image represents about 1 kilometer on the ground.
The satellite can only measure temperatures up to about 56 degrees centigrade. Now, clearly volcanoes are hotter than that. But that 56 degrees is the averaged temperature over that entire 1 kilometer pixel. So you have a bunch of snow, cold rocks there at around 0 or minus 10 centigrade. Then you have the hot stuff at who knows what, 200-300 degrees. And you add all that up and sort of average it, integrate that temperature, and you get this 40-50 degree in the satellite image. It's a lot that can happen within a kilometer. You can have fissures, you can have lava flows, fractures, hot gas, mud flows, and we have a temperature that sums everything up in that kilometer, and we don't really know what's going on in there. So one of the ways we solve that problem is with the infrared cameras. A FLIR, a forward-looking infrared radiometer. The FLIR camera is, put simply, an infrared digital video camera. We can measure from each image the actual temperature at each pixel in the image of our target. It makes corrections for the atmosphere, the distance to the target. The closer you can get, the better your resolution, although we try not to get too close. That's what zoom lenses are for. But we use it to gather the temperature at a volcano, preferably from a safe distance. The way we used to do this in the past was you had a thermocouple, a little metal rod, and you'd wear a flame retardant suit, get as close as you could, stick that into the lava and get a measurement. Fortunately, we don't have to do that anymore.
Thermal data is an important tool for understanding what happens before a volcano erupts. Combining satellite data and information from the FLIR camera makes it possible to better anticipate eruptions like the one at Shushalden. It is one of the most active volcanoes in Alaska's Aleutian chain. A 2-month record of thermal changes alerted researchers of an approaching eruption. This type of thermal monitoring of remote volcanoes is vital for providing timely warnings that reduce risks for air traffic and local residents.